Hi, welcome to Section 1, Swift Primer and Intro to Functional Programming. The first half of this section will serve as a Swift review, where we'll be sure to highlight many of the important language features that make Swift unique. During the latter half of this section, we'll introduce functional programming, which will be a reoccurring theme throughout this course. Now, let's move on to the first video of this section, Swift Review, Operators, Types, and Strings, to begin our Swift overview. In this video, we'll touch on some of Swift's unique language features. We'll begin by discussing Swift's operators, types, and typecasting. We'll also be sure to spend some time discussing Swift's unique string type. One of the first things we notice in Swift is the heavy use of constants. We first define our stored properties as constants and only change them to variables when mutation is necessary. In fact, the compiler enforces this behavior with warning messages. Now, this is actually a good thing for our application's performance because it encourages us to use variables sparingly. Since constant values are guaranteed never to change, they are considered thread-safe and can be optimized by the compiler, making our code run faster. Swift offers all of the common operators that we'd come to expect in a modern programming language, including an enhanced version of the modulus or remainder operator, which, unlike many other languages, allows us to perform remainder calculations on floating point numbers. As with many other programming languages, performing calculations with very large numbers can cause overflow errors. Of course, Swift, being a safe language, offers a set of overflow operators that allow for extra safety when working with numbers that are either too large or too small. For example, if we assign an unsigned int 16 with a max value of 65,535 and attempt to increment the value using a simple operator, we'll get an error and our program will crash. However, if we attempt the same operation while utilizing Swift's overflow operator, we'll receive the value 0 rather than a runtime error. Swift also provides two useful range operators that are not found in the C language. Range values are shorthand for expressing a range of values. The first range operator ranges from A to less than B. The second ranges from A to B. We can use range operators like these with Swift's for-in loop to iterate over a given range. For example, we can write, for I in 1 through 5, print 3 multiplied by I results in I times 3. And we see our program iterates over each item in the range, much like a C-style for loop. If an operator we need doesn't exist, we can either overload an existing operator or create a new operator of our own to suit our needs. For more information and resources on Swift's operators, be sure to visit this video's resource page. Swift's basic types can be used just like their C counterpart types. However, in Swift, types are first-class objects, complete with their own initializers, functions, and properties. In addition to Swift's native types, we can always create our own types or import types from the Foundation library. Of course, we still have access to all of the Objective-C types, and many will automatically bridge from Swift to Objective-C's NS types for us. For example, if we take Swift string and assign it to NS string, the compiler automatically bridges from Swift to Objective-C's NS string. Casting from Swift to Objective-C, however, requires a typecast. Fortunately, Swift offers two useful typecasting operators to help us with this, the is and as operators. Type checking with the is operator is a way for us to check the type of an instance, while the as operator is a way for us to treat a given instance as a different subclass or superclass from somewhere else in its own class hierarchy. In functional programming, types can become very complex. Fortunately, Swift offers type aliases which allow us to create our own alias for any given type. Here we have a function with a type of takes two doubles and returns an int. We can simply assign this function type to a new alias and use it in place of our function's original type. This can come in pretty handy when working with very complex types. The string type is exceptionally noteworthy in Swift, granting a safe and efficient means of iterating and splicing strings with its native start index and end index properties. Swift even provides a subscript that takes an index to fetch a specific character. If you need to insert a string into another string, you can do so by utilizing .insert and passing it a string to insert along with an index to insert it at. Removing a range of characters from a string can be done by calling .removeRange and passing in a range. In fact, string is loaded with so many features that it actually meets all of the criteria necessary to conform to collection type, which would give us access to array-like functionality such as iterating through a string using a for-in loop. We could easily arrange this behavior by adding a simple extension method. This alone gives us the ability to iterate over a string with a for-in loop as shown. Having said that, a string is not a collection by design. Unlike strings, collections have a known beginning and end, which allows for random access, and iterating over them can be done reasonably fast. While on the surface, we may perceive a string to be made up of a simple sequence of characters, under the hood, each character is composed of Unicode scalars that might require multiple code points composed together. The reason I've decided to point this out is because it can be tempting to treat Swift string as a collection type to gain access to more methods of string traversal and manipulation, but doing so can come with drastic performance penalties and even bugs. We'll be discussing performance in depth in Section 7, Performance Optimization and Intro to Algorithms. In this video, we began reviewing some of the fundamental characteristics of Swift regarding operators and types. In the next video, we'll discuss Swift's collection types, arrays, sets, and dictionaries.